Welcome, this is the AP Physics Workbook solution. Here I'm covering Unit 3, Circular Motion and Gravitation. Here I'm covering Section 3.F, which is on the horizontal circle. Here's the scenario. A police car of mass m moves with a constant speed around a curve of radius r. The car is, from your point of view, is coming out of the page and is this process of turning towards the left side of the paper. Let me draw that for you. Okay, he's making a left, so imagine the curve like this. Okay, all right, that's the way the curve is. Okay, and he's about to make a left. The car is moving as fast as it can without sliding out of control on the flat roadway to respond to an emergency. The maximum safe speed is v naught. The coefficient of static friction between the car tires and the roadway is mu S. Again, it is considered static friction because the tires are revolving. Okay? All right. So, okay. First one. The dot at the right represents the car. Draw a free body diagram showing and labeling the forces exerted on the car around the corner. Make sure you draw the lengths correctly. All right. So, on my right hand side are the notes that you can find in your textbook on this section. And notice there are three forces that are acting during the turn. Okay, part A is from the top, from the front view, and part B is from the top view. Okay, so here you're doing it from the front view, and again it is making a left. Okay, so the force that is pushing it in, that is horrible. The force that is pushing it in is going to be the force of friction. Force going up, 1, 2, 3. So I'm going to make that 1, 2, 3, 4, or longer. So 1, 1, 2, 3, 4, 5, 6. And this is going to be force normal. So if this is 6, this is also going to be 6. 1, 2, 3, 4, 5, 6. Okay. Force normal and and force gravity have to be the same here. Good. All right. The next part, again, it's exactly like your notes, okay? But this time it's making a left. All right, so part B. Suppose that the car encounters a wet section of the curve of the roadway so that the section of the curve has a coefficient of friction less than the mu s above there, okay? Now, what happens here? You are going to mark the maximum safe speed that the car needs to make this turn. Okay, so the first one, is the new velocity going to be less? Is the new velocity going to be the same? Or is the new velocity going to be greater than? Okay, so I want you to think about it in terms of this notes on the right hand side here for this part. Okay, let me read it to you. To make you go in a curved path, the seat or the friction or the door on the car, which is directly in contact, exerts a force on you. The car also must have a force exerted on it towards the center of the curve if it is moving in the curve. So, on a flat road, this force is supplied by the friction between the tires and the pavement. So, the force that is inward is caused by the force of friction. Okay? So, what you can write here, okay, first, based on this idea, is supplied by the friction force. So, you can write the force pulling the car on the curve okay, is called the centripetal. The force pulling the car on the curve is the friction force. Okay. And we have a name for the force that's pulling the car on the curve. We have a special name for that. We call that the centripetal force. The centripetal force here is just the sum of the frictional force. Remember from the workbook sections before this, the centripetal force is a combination of certain forces, and in this case, it is just the friction force here. Okay, it's just the sum of the friction force here. All right. So now the friction force, the friction. Did I spell friction right? Yeah. The friction force um, depends on the, I don't know how to type that, depends on the mu. Okay. And we know that if the if if the whatever symbol that is, mu, if the mu is smaller then the centripetal force is smaller, so the V is smaller as a result. Result. There you go. So let me just write that mu symbol. There you go. Good. So if the mu is smaller right here, it is less than. Okay, so it is going to be this one. All right. The new velocity is less than the original. All right. So please understand that this translates to new velocity. This is the less than symbol. Original velocity. There you go. Good. All right. Next part. Suppose that the car arrives at another section of the road and it curves and it makes a radius curvature greater than r. Okay. You are going to mark the speed that is responsible. So here it is a bigger curve. Okay. Let's see how that would change. You're not looking at any equations quite yet. All right. So what you can say here is that let's just look at the how the R affects the force. Okay. So how does the R affect the force? Okay. All right. So with so another question you could ask yourself here is, I can even type it out here. All right. Is how does the radius affect the speed of the car during the turn? Okay. All right. So with a larger radius, the car has to travel further, okay, because it has to travel further, okay. This should make sense, okay. This should make sense mathematically. Let me write it right here, okay. Remember, the distance that it travels is based on the circumference, right? If this is r, the circumference here is 2 pi r. But if the radius here is bigger, it is, so here the circumference is bigger here. It's going to be 2 pi big R. Okay, so notice that this is where the car travels further. So the car has to travel further. Because the car travels further, okay, the car must travel further to change the direction, actually the same amount. Therefore, the car can actually go faster with the same force. So with a larger radius, the car has to travel further. So with the same force, please understand this, with the same force, okay, with the same amount of force, the car, okay, because again, force can be different sometimes. But here, given that they're taking the turn with the same amount of force, right? The fact that now it is a longer distance, right? The car has to go faster in because right? The car has to just go faster. Okay? So think about it. For you to cover this distance at the same time, you would actually have to go what? Faster, right? This would be to cover right here. Let me write right here, okay? Because some of you might not see it. To cover to let's say let me write this for you. Let's say this is the start, okay? And this is the start. And this is the end. This is the end, okay? To finish, right, the turn at the same time, the car has to be faster on the curve with the larger R because it covers more distance. There you go. This is a simple way to think about that. All right? That is the reason why here you can think about it that way, okay? The car has to go faster. Okay? So here the car has to go faster. So what can we mark here? We can mark that the second to velocity is greater than the first velocity. So the velocity 2 is greater than velocity 1. Good? All right. Good, 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 good. So here, let me just bring this down because you're going to need it, right? Okay. You're going to need it down here. And here's the equation for it. All right. Here I just threw in some numbers. You don't even need the numbers. So let me just take out the numbers here. All right. So you're going to derive an expression for the maximum safe speed that the car can make to make the turn. Okay. All right. So let's start with what you have. Okay. So in your formula sheet, you have this equation. You have, I think, A is equal to summation F over M. So just multiply the M across. Right? So you have MA is equal to F. Okay? We're going to make this around the curve. Okay? So you can write this if you would like. MAC over, and this is just in the horizontal. Okay? Again, AC stands for the centripetal acceleration, and Fx is just the force in the horizontal distance. All right? So what this breaks down is M is going to be equal M. The A centripetal acceleration is defined as v squared over r. All right? And the only force that is supplying the centripetal force here is the force of friction. So force of friction, right? But we know what the force of friction is. We know that as mu times, we know that that is mu of the normal force, okay, times the normal force. All right, so let's see what we can do here, okay? So it looks like exactly like the way this equation is set up in your book if you take a look, all right? Okay, now our goal is to solve for v, okay? All right, so, well, there's a couple things that you can do here, okay? Understand that n is just mg, so you have that, all right? Okay, oh, let me just bring this down, okay? This is just me making the substitution. So this step is just me making the substitution. The m's cancel, so it's just v squared, uh, v squared over r is equal to mu g, okay, times r to both sides, times r to both sides, mu g r, square root it, mu g r, you get v is equal to the square root mu g r. All right. Okay. So here you go. This is the deviation. Good. If you want like the explanation, I could write it for you if you want. This is the equation on the formula sheet. Okay. This is now I'm gonna do um, multiply m to get multiply m to both sides. Okay. And again, this is the define the acceleration on the curve. Right? That's why the a is AC technically now. Right? Then here I make the substitution. Substitute the acceleration on the curve as v squared over r squared, v squared over r. Okay. I'm just doing a lot of steps to just show you everything. You don't need all the steps. Now you want to define the force of friction as mu times the normal force, and here it is on a horizontal distance. It's on a horizontal distance. So the normal force is mg. Alright, because a long time ago, this problem we used to do it on a bank, so the normal force sometimes had a sine and a cosine part to it. Alright, the mass cancels. Do some algebra here. Multiply by r to get the velocity alone. Square root both sides to solve for r to v. I mean, this should be a v then. Okay. There you go, to get v alone. All right, and there you go. That's how it should look like. Okay. Now, I explain how your expression in part C. This is what we have, and again, This is, if you see in your book, it's done the same exact way, but for them to finish it, right, they would just have to multiply by RG to both sides, right? It's going to be the same thing. V squared is equal to RG mu, square root it, RG mu. You get the same thing, RG mu. Okay, there you go. All right, so explain how your expression in part C supports your answer in part I. So here we saw that a smaller mu, how does that affect the velocity? Okay. All right, so I can show you the math if you would like. Right? So just let's just plug in, like, let's just half it, right? So v is equal to the square root, and let's go with like half. Let's go with like half. Or let's go with the decimal. Decimal mu times gr, right? Which is a smaller one. Okay. How does this affect this? Well, it's going to be the same thing. What is the square root of half, right? It's going to be, right? This is going to be a super small number. Okay. Right? The 1/2 here just makes this smaller. That's it. So what you could say here is that a smaller um, coefficient coefficient of friction means a smaller coefficient on the right hand side of the equation means the left side of for the velocity has to also be smaller. Has to also be smaller. Okay? So the left side goes down, so the right side goes down for mu, so the left side v goes down. Okay, so we were right here. All right, smaller mu means a smaller v. All right, what about here? We want to now increase the r for part 2. So here we can write, again, if you want to see it mathematically, how does that look like? Here's the original, mu gr, but the r here is going to be, let's say, bigger. So it's probably going to be this, something like that. Okay, do you see how this went up? So we can write a larger radius on the right hand side of the equation means the left side for velocity has to be greater. Okay. All right. So the right hand side goes up, so the left side has to go up. There you go. That should be left. Okay. I misspelled that, but this should be left. Ugh. And this should be. All right, there you go. That would be the complete answer, okay? And is that it? Yep, that's it. That is all your solutions for 3F.